Let's talk about computing the area between curves. I have two examples that I'll do in this video. One is going to be with respect to x, and the other one will be computed with respect to y. And both of these, I'm just going to set up the definite integral for the answer. I'm not going to spend time actually computing, but they would all end with antiderivative, plug, plug, subtract. Okay, so the first one is the area between y equals x and y equals x squared from x equals 0 to 2. So I have provided a rough sketch of these two graphs. Y equals x is a straight line that goes through 0, 0, 1, 1, 2, 2. And then y equals x squared, we have at least half of its parabola that goes through 0, 0, 1, 1, and 2, 4. So if the x values are given 0 to 2, that means we have kind of two distinct pieces of area to compute. We're going to do the area of this little piece here, and then the area of this sort of triangular chunk over here. So I'm going to have the sum of two integrals to compute this. I also want to point out that this one we know that we can do with respect to x, because for each of these two regions, there's a clear top function and a clear bottom function. So anytime we're integrating with respect to x, our integrand will be top minus bottom. Also notice before we keep going that the point of intersection between the two is clearly at 1, 1. If we weren't sure about that for whatever reason, we would set x squared equal to x. Let's actually do this out. Let's say just in case we don't realize that they intersect at 1, I would set one formula equal to the other. Put them both on one side, factor out the x, and I get 0 and 1 as the x values of intersection, which we can see in the picture right here and right here. Okay, so this area, like I said, is going to be the sum of two definite integrals. The first one will integrate x equals 0 to 1. And I'm going to have my top formula minus the bottom formula with respect to x. So the top formula here is the blue line, that's y equals x, minus the bottom formula, which is x squared. And then we'll add the integral from 1 to 2. 1 and 2 are the x values that I'm covering. And then I'm going to have top formula, which is now x squared, minus the bottom formula, which is now x. So I have to separate these out into two pieces because they're not using the same top and bottom choices for each. And then from here, I would do antiderivative, plug, plug, subtract for each of them, compute a number, and then my final answer is those two numbers added together. And they should both come out positive because of the way we split this up. This brings us to our second example here. The area between x equals y squared minus 4y and x equals 3y minus y squared. This is a much more intimidating problem. We can see right off the bat that x equals a formula of y. Both of the curves are given that way, which suggests I'm probably going to have to integrate with respect to y, but not necessarily. We'll sketch these out and kind of see what we're working with. All right, so I also want to use this as good practice for sketching our own in case we ever have to. Let's start with the first one here, y squared minus 4y. I'm going to factor this. This is y times y minus 4. So this is an upwards opening parabola. So upwards when it's x equals y squared is this way, like that. So upwards opening, and it will go through 0 and 4 as y-intercepts. So when y equals 0, x is 0. When y equals 4, x is also 0. So 0 and 4 as intercepts, and it's going to open upwards. It's going to be enough of a sketch to get by, at least for now. I don't know quite how low to put that vertex, but it's not really going to matter for our purposes. So I'm just going to label this before I keep going. This is x equals y squared minus 4y. All right, now for the next one, I have x equals 3y minus y squared. This is negative y squared plus 3y. I can factor out a minus y, and I get y minus 3. You don't have to actually factor out the negative, but I like to do it this way so that I can see it's a downwards opening parabola because of that minus y squared. So now we're talking this way, and it will have y-intercepts at 0 and 3. So that's 0 and 3, and we're going to open this way. So if we want to compute the area between them, and again, I'm just going to set up the definite integral and not compute here, we're talking about this area. Now, this isn't impossible to do with respect to x, but you would have to break it up into several integrals, right? So for some chunk of this, like here to here, you would have top minus bottom being the top and bottom of this curve when it's back solved for y. And then from here to here, kind of before the y-axis, we would have top of the red minus bottom of the blue. And then we'd have a third chunk over here where it's top of red minus bottom of red. So we'd have 3 separate integrals to compute. We'd have to back solve each of these for y, which is not particularly easy. It's going to be much, much smoother if we integrate with respect to y. So if we're integrating with respect to y, meaning there's a dy at the end of the integral, what we'll set up is always the right curve minus the left curve. It's right minus left, even though this kind of looks wrong, given that this is on the left and this is on the right. But it's always right minus left because a right more, like a point that is more towards the right has a higher x value, and a point to the left has a lower x value. So we're still doing higher minus lower for total distance. It's just we're thinking x values instead. We want the right and left formulas to be given as expressions of y. We'll put a dy at the end, and then the bounds of integration will also be y values. The reason that this is going to work more smoothly than the 3-piece dx way is because if we look at it as a right edge and a left edge, we can do this in one single integral, right? The red curve is forming the entire right edge. The blue curve is forming the entire left edge. So we can do this all in one, which is much nicer. So I'm going to have the integral of the right formula, so that's the red, 3y minus y squared, minus the left formula, which is the blue, y squared minus 4y. Those parentheses are mandatory. I'm going to have to distribute this subtraction in the next step. I put a dy at the end, and then the last piece of the puzzle is what the bounds of integration should be. So in this first example, these bounds of integration, 0 and 1, 1 and 2, were mostly just coming from us looking at the picture and seeing it. The 2 was a provided part of the problem. Here it's just whatever area is between them. And certainly y equals 0, we can see that they're both crossing through the origin. But this upper number here, the y value of this top intersection point is not clear. So this is one where we have to do it this way, where we're computing the intersection instead of just seeing it from the picture. So I'm going to set these two formulas equal to each other. I want to know where y squared minus 4y equals 3y minus y squared. Okay, we're expecting it to be some kind of number between 3 and 4 based on my picture. I'm seeing quadratic pieces running around, so I'm going to pile everything on one side, make the other side 0. If I add this y squared over, I have 2y squared. Minus 4y minus this 3y is minus 7y. I can factor out a y. And I get 2y minus 7 inside. So y equals 0. Ooh, I said this was on the screen. There we go. So this y equals 0 is this intersection point right here. And then this other one is 7 over 2, which is 3.5, which makes complete sense given what we were seeing in the picture. This is exactly how we want to see these bounds, 0 and 7/2. These are the y values of the two intersection points, which is what we want because we're integrating with respect to y. Whereas in the first example, we were using x values of intersections because we were integrating with respect to x. So these are the y values. So I'm going to put 0 to 7/2. I could leave my answer here, In an actual test problem, you may be asked to compute the entire integral. So I'll go a couple of simplifying steps here just to show how I would get it to a doable point. I'm going to keep my bounds, distribute the subtraction, and then combine like terms. 3y plus 4y is 7y. And I get here. So then to do the full computation of the area, I would do antiderivative of each part, plug this in, subtract the two, and you should get your total area.